Hi, everybody. My name is Dean Ward, and I am a principal developer on the architecture team at Stack Overflow. I'm here today to talk to you about Stack Overflow for Teams. In particular, how we took a pretty stinky 10-year-old monolith, that is the Stack Overflow codebase and architecture, and scaled it to extreme multi-tenancy. Now, Chris mentioned this briefly, but for those of you who are unfamiliar with Teams, it's part of our product suite that provides private Q&A. We got kind of two main editions. You've got the Enterprise Edition, which runs on a customer's premises, or it can be hosted by us in Azure. And then we have the basic and business tiers, which are hosted as an embedded part of Stack Overflow on our own infrastructure in our own data center. And that's the part I'm going to be talking about today. So to kick off, let's talk a little bit about the numbers on the public side of things. We're already running a pretty high scale with a relatively small amount of infrastructure. So we have a mere 9 web servers handling around 5,000 requests a second, and we get around 8 to 10 billion hits a month. However, we're only doing that with about 10% average CPU on our web tier. So in theory, we could run on a lot less machines. We choose not to for resiliency reasons. Our most hit page is the question show page. That's the page you hit when you come from Google and you see the questions and the answers. And that renders in 20 milliseconds. Now, people normally boast these kind of numbers and it's backed by heavy duty cache and all this kind of stuff. This 20 milliseconds is going to the database, getting the questions, answers, the comments data, molding it into view models and all the rest of it, and splurging it out as HTML onto the page. That takes 20 milliseconds on our side at a sustained 5,000 requests a second. That same web tier is also dealing with about 500,000 WebSocket connections, which are dealing with real-time messages, things like inbox messages, reputation updates, that kind of stuff. And our SQL servers are dealing with about 10,000 batches a second. Our Redis servers are dealing with about, pick up the phone. Our Redis servers are dealing with about 30,000 commands a second. These are peak numbers, but it kind of varies throughout the day, but not too drastically. From a data perspective, we're not particularly big data. We prefer to call it medium data. It's not massive, and it's not tiny. But we have around 60 million posts across the whole network. Stack Overflow has the most. It has 17 million posts of any individual site. And the Stack Overflow database itself is around 4 terabytes. So again, not massive, but not tiny either. A key thing about the Stack Overflow architecture is it's already built for multi-tenancy. We obviously have a whole bunch of sites already. But every single Stack Exchange site runs off a single application pool in IIS. So there's just 9 application pools across the whole thing. We just use the host header to switch context. So that context being, hey, what database do you connect to? What kind of site settings? That kind of stuff you get. Now, we can do all this with relatively little hardware because of a long ongoing obsession with performance. We consider performance a feature. It saves us money. It keeps everything up and running on a pretty kind of shoestring set of kit. And so this brings me on to our architecture. Now, we have not a particularly complex architecture. It's simple, and we value the simplicity because it's operationally simple. This means during an outage, there's not that many places to mess with. So you can see on the outside, most requests come through fastly. They hit our external load balancers, which are running HA proxy. HA proxy TLS offloads, and that hits our web tier. The HA proxy side of things is dealing with web requests, and it's also dealing with WebSocket requests. So the 500,000 WebSockets are coming in via there and hitting the web tier. The web tier itself hosts a number of apps. We got the Stack Exchange network itself. We have the talent and job sites. We have chat, and a small number of kind of related services, things like the WebSocket server, that kind of stuff. And you can see back here, there's the service tier. They're both labeled as load balancer A because it's actually the same load balancer. It just kind of talks to it internally instead. The service tier, there's only 3 of those boxes, and that's kind of hosting internal-only services. So we have stuff like our tag server. Tag servers are a highly optimized way of querying tags. It's basically a bunch of inverted indices. And whenever you go and visit, say, a list of questions or anything that's tag related on Stack Overflow, the tag server is dealing with that stuff. The other services that are on there are things like Stackmail, which deals with all of our outbound email and deals with that in a consistent way. So it deals with opt-outs and all that kind of thing. And then finally, we have a service called Providence. Providence kind of trawls through our traffic logs and then uses the data it gleans for targeting on the job board so that we can target jobs better. From a database perspective, we're running Microsoft SQL Server. We're largely a Microsoft stack. Pretty much the only thing on there which isn't Windows-based are the Elasticsearch and Redis boxes. But we're using SQL Server as our primary data store. We have two main clusters, these ones down here. Those two clusters are serving the majority of the sites that are on the web tier. And each cluster is configured as an always-on availability group. We have one master, which is, I don't want that. No, thank you. Let's get rid of that. We have a primary box, which is used for writes, a secondary box, which takes some reads in the DC. That's generally for kind of background task stuff because you have a latency between writing and actually reading. And then we have another secondary in a failover data center, which is just used for failover purposes. From a search perspective, we provide full text search across the Stack Exchange network, across chats, and across our talent and jobs products. That's all hosted by Elasticsearch. And then Tag Server, which is hosted on the service tier, that thing is also dealing with. It's kind of a search service, but for a highly optimized use case. We have, what does it say up there? 9 instances of Redis. They're configured in a primary secondary chain. So we're not using the Redis cluster. We're actually just using the old style kind of chaining mechanism. So there's 2 in the primary data center, and then the 2 in the secondary data center are chained to the primary. We use Redis for caching, obviously, also for queuing and distributed locking as well. And finally, this whole thing is mirrored in a secondary data center in Denver, Colorado. And we use that just for failover purposes. It's essentially the same, just some of the numbers are different here. So we have less Elasticsearch instances, less Redis instances, etc. And so that's pretty much all there is to that. Now, when it comes to teams, we have a whole set of different challenges. The Stack Exchange network itself is largely public. We do data dumps, which have the PII stripped, and those are uploaded to archive.org so people can go and mess with our data and stuff like that. So the infrastructure that I just showed you over here, it's fairly open. Most of our developers have access to the servers in here, and they use that to effectively do their jobs. But teams has a whole set of different challenges. Number one is security. And that's because customers expect their data to be under lock and key, right? We don't want to reveal proprietary secrets to the world. And so we need to adjust our architecture accordingly. Teams itself is treated quite differently to... No, I've just read the wrong part, so I'll back up a little bit. So from an infrastructure perspective, there are a lot of protections in place. We have protections at the infrastructure level, so firewalls, which are preventing most access in, plenty of access controls, and a whole ton of auditing and monitoring. Now, that's not to say we don't have auditing and monitoring on the public site. It's just kind of less important. It's mostly public data, right? From the application level, there are authorization checks on the way in and on the way out. And there's more auditing, more verification, and generally a policy of default deny. If anything goes wrong, no, that's it. One of the key things about teams when we were developing the product is engagement. So as a result, Teams is embedded in Stack Overflow. I kind of wish I did a screenshot, but in effect, if you've used Teams, it's the regular Stack Overflow Chrome, but on the left sidebar, you see a list of the teams that you're in, and then you click into that. So that means that Teams is treated somewhat differently than a regular Stack Exchange site. It's essentially treated as a child of a parent site, and so we can have this hierarchy if we want to. That does in effect mean, in theory, I'm not going to say this is something we're ever going to do, but Teams could run under server fault, it could run under super user, it could run under bicycles if we wanted. We choose not to run it under bicycles. It's not that popular. But that comes with its own set of challenges. We have to get the data interleaved with data in the regular public site, but in a way which is very efficient. The next one is scale. I mentioned before that we have 400 Stack Exchange sites. Teams is a completely different level of scale. We're talking, we want to get to 200,000 tenants next year. The year after that, probably 500,000 and keep on growing. That causes problems in its own right, but the key difference with a team is that it is far smaller. A regular Stack Exchange site might have thousands of hundreds of thousands of posts, but a team may have hundreds or thousands of posts, so it's much, much smaller in terms of data. So one of the key questions we have is, can we reuse that same code base, but it's a very different kind of scaling need. So can we scale out rather than up? And then what about the infrastructure itself? How do our SQL servers, our Elastic servers, our Redis servers all handle like tons of tenants? And then the big one, when you're building something, you don't really want to spend that much money on it because it's not making any money. So how best could we prove out our product without burning tons of dollars in getting everything spun up? So this is where we were before. This is our DMZ. And then we introduce a new secure network, which looks almost the same. So largely speaking, the DMZ itself remains the same. Any routes that come in that need to touch sensitive data, things that are in a team or things that are associated with teams, they're forwarded to a secure zone that we affectionately call the CFZ, which stands for Channels Firewall Zone, but for some reason it's morphed into Channels Fun Zone. Mostly because of how much fun we had developing it. But Channels was actually the original name of the team's code base when we started building it. Sorry?
It's mostly entitlements and ACLs.
Sorry, I missed that.
It's mostly entitlements and ACLs.
Yeah. Yeah. The architecture itself is a mirror of the DMZ, right? But it has far, far more restrictive firewall rules. The only thing that's allowed in HTTPS. And the auditing is upped a good bit more, and only a handful of employees in the entire organization are allowed to access this network. So I think there's like 5 or 6 people that actually have access to anything in here. And then within the network, okay, so in the DMZ, we're not currently TLS everywhere. That's where we want to be. We're not quite there yet. In here, because it was built from the ground up, everything is TLS within. Now, the key difference with this, everything over here is physical. Pretty much everything over here is VMs. And the reason we did that is we had some big-ass VM servers and a bit of capacity on them, and so we spun up everything as VMs. The only thing that isn't a VM in here is the SQL server, the one that's labeled channels there. That's actually physical, and the reason that's physical is we needed a ton of local SSDs and a ton of memory. And the reason for that is when you have a load of tenants hitting a thing, you kind of need that, and the VM servers couldn't provide us with that capacity. So anything that handles sensitive data lives in this network. So some metadata lives over here, but the metadata isn't sensitive, right? It's just kind of general information about things. Anything which is actual content, anything which holds customer data lives in here and is locked down. So how does this work? With a dash of crazy, I think is probably the best way of putting it. So that's the architecture. I mentioned before that we want to embed this thing in Stack Overflow. Now, routes that need to be forwarded are forwarded via the application itself. We don't use HA proxy, we don't use Nginx as a forwarding proxy. It doesn't have enough context on the kinds of things that we want to do, right? So we use an application level proxy that understands more details about the request. And then on the way in, this yellow line here, we do authorization checks. But as soon as we're in here, we do the authorization checks again. You can't trust the authorization checks out here because somebody may have tampered with something that you're using for those authorization checks. So we perform them again in here on data that's held in here. That means that if anything goes wrong along the way, you're shut down. You're not getting in. Complete lockdown. Now, that forwarding call adds contextual information along the way as to, here's the account that was accessing, here's the site it was trying to access, a few other bits and pieces, and then that's used to verify things, but used to verify with information that's stored in the CFC itself. The thing that's running on the web tier over here is actually an instance of the Stack Overflow code base, but instead of being configured to know about the public sites, it's configured to know about a bunch of private sites instead. So to the application, the way we've built this, the application doesn't change how it's dealing with the request. It looks like a regular browser request, except just before we send the request back, we cherry pick out bits of the HTML into another layout, and then the DMZ side of things can interpret that and interleave things with the Stack Overflow Chrome. This is absolutely batshit crazy, I'm aware of that. But there are reasons for this. It allows us to gain a great deal of efficiency. But to the application, it means our developers don't have to context switch all the time. They're just writing Stack Overflow features, Stack Overflow code. They don't have to change how they're developing stuff unless they actually have to touch that bit. The reason we do this, it means we're effectively streaming bytes directly from the CFC instance of Stack Overflow to the DMZ instance, which means that we can fairly efficiently write the bytes into the right places on the page. This greatly reduces allocations. Now, most people ask, why on earth aren't you using an API? Again, allocations. When you're serializing, deserializing gobs of data everywhere, you're building up allocations. A lot of stuff ends up on the large object heap because you're dealing with a lot of large objects. And so inevitably you get garbage collection stalls and then everything grinds to a halt, which is just terrible. So the big problem with this is it's really, really highly coupled. So if we make changes in this CFC thing, the DMZ thing needs to understand what those changes are. This means that forwards, backwards compatibility is very, very hard to achieve. You need to synchronize deployments and all this kind of stuff. We're aware of this problem. It is something we plan to fix in the future, probably sometime next year. It's just not a particularly high priority. It hasn't bitten us too hard. It's bitten us once or twice, but not the end of the world bitten us, you know. So that's fine. The next big thing is sharding. Naturally, when you're dealing with hundreds of thousands of tenants, you have to deal with sharding. So we primarily shard in two places, SQL Server and Elastic. We shard in Elastic on a per tenant basis. Now, when we started testing this, we started doing this on a per database level. Bad idea. The reason it's a bad idea is SQL Server gets very, very angry when you spin up thousands of databases. Notably, things like backups become difficult. All your tooling breaks, literally all your tooling. You try and load SSMS and it takes 10 days to load the page. And things like availability groups start to fail. Your replication starts to fail. Well, they cannot deal with hundreds of thousands of things being replicated. It's just not in the kind of design for it. So we've opted to shard based upon schemas. We have 10,000 tenants in an individual database. That means that still, yeah, I saw a face there. You still get tooling issues, but they're not as severe as if you had hundreds of thousands of databases. But we have tooling ourselves which can deal with this gracefully. Backups are still a bit of a pain. If you have a customer that has gone away and they want their data back and it's like in cold storage, you have to go get it and cherry pick out bits from the backup and it's a pain in the ass, but we try not to do that too often. Now, to make that the whole schema-based thing work efficiently, we maintain a large pool of pre-provisioned schemas, and then the act of actually creating a team on the site and paying for it, that goes and claims one of these pre-provisioned things. So we keep like a buffer of 1,000 things, and then we're just gradually replenishing that buffer as it gets eaten up. Provisioning itself is a very, very heavy-duty thing. It doesn't take drastically long, but when you're operating on the order of milliseconds for requests, something that takes 5 seconds is not cool for a request. And so the other aspect to that is provisioning is very, very highly privileged. So we try and keep that in a separate process locked away with a highly privileged account that is just called via a service. Elastic is sharded every 5,000 tenants. And we originally tried to do individual indexes. Elastic also gets very angry. So what we do now is there's a single underlying index and it uses filtered aliases to ensure we bring back just the relevant data. When we did indexes per tenant, we found that Elastic started to eat CPU and RAM just sitting idle. And the reason for that is that it eats a lot of cycles just maintaining those indexes. So Elastic has leucine shards underneath the hood, and it's costly to maintain those shards. Our new approach using many tenants per index is far more consistent with CPU and RAM usage. We're kind of bubbling around at like 5% or something now. But we don't trust filtered aliases. Elastic doesn't have built-in security unless you have add-on packs and stuff. So we guard against filtered aliases being messed with by having application level checks to make sure the data we get back is actually genuinely for that team. Don't trust anything. From a security standpoint, I mentioned before, we do authorization checks on the way in, and they're re-verified prior to being allowed access. If there's any doubt at all, we deny, and there's an error log, which a developer has to go and investigate. Was this somebody trying to mess with us? Is this a genuine problem? Something like that. And then from a kind of slightly different security side of things, we don't allow any third-party JS to run on Stack Overflow. If we do, so I'm thinking like ads, things are sandboxed in an iframe and locked down. They're only allowed to run certain things. I'm not going to go too much into ads. That's been a whole thing recently. So we'll skip that. But with the third-party JS, the problem with that, and judging from some conversations I've had recently, not enough people realize it. If you allow third-party JS from an untrusted domain to run on your site, it has access to all the things the user does. So if you are running a secure service in any way whatsoever, you will allow that JS to exfiltrate your customer's data. That's not a cool place to be. Workarounds are that you vet the script and then put like a SRI things on the element. But that's not necessarily very scalable when you get versioning problems along the way and all that kind of stuff. So we do not allow any third-party JS. The one exception is Google Analytics. We trust them for some reason. However, all data is scrubbed prior to it being relayed to Google, so we don't send any content up, no titles, no tags, no usernames, no anything. The next one is scaling optimizations. I mentioned we're running on VMs, and we've never run hundreds of thousands of things before, and we were kind of nervous of maintaining performance levels as we scale. The good news is that because of our previous careful work, we've actually not had any issues right now. We're still running roughly 20 milliseconds even on that virtual architecture. So that's pretty good. But the issues that we have seen are where we're doing operations that are going across all the things. And the problem there is that it's an ON problem, right? You just, every time you add a thing, you have to do work on it. So for example, we have scheduled tasks that award badges to people. We have scheduled tasks that send newsletters. We have scheduled tasks that index posts into Elasticsearch. All those things are painful when you get to any level of scale. The easiest way we've found to eliminate a lot of that cost is to keep track of the last time the thing was active. What we found is that a team that is inactive probably doesn't need anything doing to it. And so as a result, you can skip a good chunk of stuff. So based upon the tasks that you're performing and the last amount of activity on the site, we can adjust how much work we need to do. So what we're normally finding is that we only have to run on 25% of sites at any one time, which drastically reduces the runtime for a lot of these background things. The next problem with scale is that we found SQL Server only allows you 32,000 connections before it kind of dies on its ass. We haven't got to that level, but we had a bug, and then SQL Server blew up, and, well, that wasn't very nice. So what we've done for a lot of the intensive background tasks that need to open connections across very large numbers of sites, if we move to non-pooled connections, then when you close the connection is hard closed. And so you end up, instead of when you have a pooled connection, actually in the background, it gets soft closed. It still has a connection open to SQL Server. So if you do stuff on a lot of sites and you have different connection strings, which because we're using schemas, we do, you end up in a situation where you have thousands of connections which are probably not otherwise going to be used. Sorry, I just changed sheet. So overall, we're keeping our connection count a lot lower by not messing with any of that stuff. And the performance impact of that doesn't really matter. This is generally for background tasks that are long running and doing lots of things. The performance impact there, a few milliseconds here and there, doesn't actually matter. Our network is very fast. We have very low latency, and so that doesn't really matter so much. So that's kind of the majority of the scale optimizations we've made. But we have plans for the future as well. If you follow Nick Craver on Twitter, he's been blogging tweeting fairly regularly about .NET Core 3. We're making baby steps towards getting Stack Overflow on .NET Core 3. It's a big job. It's a legacy ASP.NET MVC app running on full framework, .NET 4.6.2. Moving to .NET Core 3 gives us a whole bunch of good stuff. The biggest good stuff, the biggest win for teams is probably performance improvements. We literally moved a bunch of stuff over to .NET Core and we got like a 30% performance improvement with no code changes. That's pretty awesome. The next one is gRPC. I mentioned the tight coupling between the DMZ and the CFC with the proxy stuff. gRPC gives us a whole bunch of benefits here. Now, it already existed. It's just .NET Core 3 kind of has this stuff baked in. gRPC allows us to do streaming from the CFC to the DMZ using basically a strongly typed API. It gives us forwards and backwards compatibility because it uses protobuf, but also because of the streaming, we keep our allocations low as well. So things are nice and clean from an allocations perspective, so we keep the same kind of memory optimizations in. Then .NET Core opens up a new layer of stuff, containers. This means that we can probably move a lot of this stinky VM stuff to lightweight Linux-based containers and run the same app. Now, we're probably not going to do this on the stuff we host in premise just yet, but it enables us to package, for example, our enterprise product up into containers and deliver an appliance to customers, which is a much better place to be. Long term, we're kind of thinking about whether the cloud makes sense. Our data center hardware is like 5 years old. As it gets older, you don't get firmware updates, you don't get security updates, you don't get all the nice things that you would get otherwise, and generally it costs more to maintain. And so, as a result, does it make more sense to move to the cloud where we don't have to worry about those costs and all that kind of thing? Now, we're going to do a proof of concept next year to determine whether that makes any sense. It's probably going to cost us more. We know that much. But, yeah, and we will lose performance. Our data center has very, very low latency. And we rely upon that a lot to not backlog. So, licenses we can get around. Nudge, nudge, wink, wink. So, there are a whole host of questions there, but those are things we plan to address next year. So in conclusion, apparently, yes, we can take this stinky old 10-year-old monolith and use it in a way which allows us to have hundreds of thousands of clients. But the only thing that's really helped us along the way there has been a previous obsession on performance and tweaking the hell out of every single layer of the stack. So after some careful choices about sharding and whether we need to do any work at all, i.e. the active teams sort of thing, we can actually scale to hundreds of thousands of teams with very little effort. Now, I don't think I have much time, but maybe one question. Thank you.